Okay, so let's get started. We have been looking at division of discrete goods, looking at division of indivisible goods, and our sort of fairness notion is NV freeness up to one good, EF1. This is our solution concept of choice, and our goal is to see and establish the existence, the universal existence of this notion of fairness in as general a setting as possible, and more ideally, in fact, develop an algorithm that finds such an allocation efficiently. So, just to recall, so a solution here, the output of the fair division exercise has to be a partition of the goods into n subsets, where n is the number of agents. So, every agent gets a subset of goods. These goods, of course, have to be pairwise, these subsets indeed have to be pairwise disjoint. So, a good goes to exactly one agent, and so such a partition, such a allocation is said to be EF1, is deemed fair under this definition if and only if the following condition holds, that if I look at any pair of agents A and B, then there is a good G in the second agent's bundle in the subset assigned to agent B, i.e. in AB, such that if I remove this good from consideration, so I look at, instead of looking at AB, I am looking at a set where this good has been removed out, then A values its own allocated subset AA more than this modified subset. So, up to one good, up to the removal of one good from the other agent's bundle, A is sort of happy in the sense of this particular inequality holds for A. So, as with NV freeness, we are looking at VA on both the left hand side and right hand side of inequality. The key difference is I am allowing you to remove one good out. Okay, so with that, we kind of went through patiently over this example where the valuations were additive, and what we did was followed like an iterative process. We iteratively assigned goods one after the other, and what we could accomplish in this example at least was the fact that if we looked at the NV graph at every stage of the algorithm, at every iteration, again, what is an NV graph? Well, we looked at the partial allocation we have so far, and we drew edges that pointed to NV among agents. So, it's a directed graph where nodes represent or correspond to agents and directed edges signify NV between them. So, as we ran through this procedure, as we ran through this example, we could always find an agent that was a source in the directed graph, and by the semantics of the construction, this source vertex was corresponded to an agent that no one else envied. So, you looked at the source agent, what you had was at every point of time no one else envied the source agent, and our rule of choice, the sort of thumb rule that we followed, was always give the next good, assign the next good to such a source vertex, to this vertex that is not envied by anyone else. And indeed that's a good rule, and let me argue again to you why that's a good rule, in the sense that if I do follow it along, then I will continue to maintain EF1. So, what I am saying is that initially I started with empty allocation, so everyone had just the empty set, these AIs corresponding to all agents were empty, so that's NV free and hence EF1, and what we are going to do is maintain this property inductively. We are going to maintain it as an invariant, and this rule that I just outlined accomplishes this task, and let's sort of go over it one more time to sort of hammer it in. So, at any stage, say I look at the NV graph, and at that stage, say by luck, so it's sort of there's a special case, if you will. Again, there could be NV graphs where there is no source, but let's worry about that later. For now, I'm saying say that your NV graph does have a source vertex, i.e. there's this agent I that no one else envies, and what we did in this procedure throughout was we took the next good, let's say G, and assigned it to agent I. That is, we we started with AI, whatever the current set of goods that were given to I, and then included G in it. So essentially said, okay, here you go, agent I, this next good G is yours. And the point was that this sort of an update, this allocation of good G to agent I maintained the EF1 property, and that's what I want to sort of argue here quickly. So observe that what ended up happening in this iteration, in this stage of the algorithm, was that I's bundle, the subset received by I, which was earlier AI and now it is AI union G, has this new good. For every other agent, J that's not I, the bundle remained as such. Like you didn't do anything, there was no update. But before the update, I had this particular inequality. If I looked at the agent J, so again, both sides, left hand side and the right hand side here, are with respect to J's valuation, then I had this inequality. Why? Well, because J was not envying I. No one was envying I, hence J was also not envying I. So this is the inequality I had up front. But note that if I now look at the new AI, which is AI, the old AI plus G, and I remove G out of it, what I get is the old AI, right? For some set I included G, I removed back, I'm back to the old AI. So this inequality here, this thing that I'm trying to put a box around, is nothing but the previous inequality with the new set of allocations, because AJ didn't change and AI just got one more good. So this is for all J, for all agents J that are not I. So in particular, this means that if I had an EF1 partial allocation, then even after I assign the next good, the new partial allocation that I have will continue to be EF1. There's one case that I have overlooked, which is what? So I need to also argue that it continues to be EF1 for I, right? So what this means is that if I look at AI, let me just write new to denote, this is the old, so yeah, this is just a rough notation. So this is what happens in the update, the AI gets you include G in AI. So what you would want to argue that EF1 continues to hold inductively. So if it held for the previous partial allocation, it's true. But that's sort of direct, because if you look at the new AI, you have one more good, right? So the only property I'm assuming here is that the valuations are monotonic, right? So note that what I have argued so far is extremely general. There's no place I have made the assumption that the valuations are additive. I have assumed nothing about the structure of the valuation except for this inequality right here, where I am assuming that the valuations are monotonic. But as far as assumptions go, this is a very generous assumption. This says, okay, if your valuations are monotonic and if you assign your subsequent good to a source vertex, to an agent who's not envied by anyone else, EF1 will continue to hold. So if you had EF1 in your previous iteration, you'll have EF1 in the subsequent iteration. So just to sort of complete this, this is by this, and this is the sort of inductive hypothesis, i.e. the fact that in the previous iteration you had EF1. So this is, so for all J there exists some, let me just call it say G hat to separate it from this good that's assigned. So this is because like before you assign this good G here, you had EF1 and so inductively it kind of marches on. So you had EF1 yesterday, you will have EF1 today, yada yada yada. So that's the sort of simple but crucial observation. Why aren't we done yet? Like why is it why don't I have what's sort of the thing that's missing is that I am still relying on the fact that as I march on through this algorithm, every time I will have a source vertex. At every point there will be one way or the other, there will be a vertex that I can happily assign G and sort of invoke this observation. So this is something we need, and as I said, in this case we make our own luck. We'll actually observe something that will allow us to find such a source vertex, find an agent that will be the recipient of the next good, find an agent that's not the source, like will not be envied by anyone else as the sort of algorithm progresses. So let's try to do that before I march on and sort of write a pseudocode or anything, like define things a bit more formally. Here's the sort of theorem. So you give me any discrete fair division problem, that is, you give me a problem where the goods are indivisible. And as I said, the only assumption, and it's a very sort of minimal assumption I'm making, is that the valuations are monotonic. Like if you actually look around at other sort of related concepts, getting something at this level of generality is typically quite hard and invariably impossible. There are negative results. But for this EF1, this is spectacularly general result holds, says that all you need are monotonic valuations. All you need is the fact that if I give you a bigger set, if I look at a superset of something, your valuation does not decrease, right? And it's exactly used here in the observation. But I'm saying all I'm going to do is sort of use this assumption. If I increase your set, the valuation, increase it in a containment sense, then the valuation does not decrease. So the first statement of this theorem is existential. It says that as long as you have monotonicity, an EF1 allocation, a fair allocation in this sense, is guaranteed to exist. And again, I am writing this as two separate statements to like emphasize the fact that there is a existential result here as well as an algorithmic result here. In fact, the way you get this existential result is through an algorithm, and so again, I'll not go into the details of it, but when I say efficiently, I mean efficient in a query sense. So think of the running this algorithm with n agents, and every time you have to evaluate the value of a subset, you just query the guy, okay, if I were to give you this, what's your value? So you have something analogous to, say, the eval queries, like modified appropriately for the discrete setting of the Robertson Web model, but a very natural query model. When I say you can do it efficiently, effectively means that you'll only bother the agents a polynomial number of times before finding an EF1 allocation. So you certainly don't need to look at all the values for all the 2 to the m subsets for any agent. And again, like something that one should appreciate as computer scientists are the gaps between 2 to the m and poly, right? For 1000 or 2000 value of m, if you have 2000 goods, the value between 2 to the power 2000 versus 2000 square is a population of Ahmedabad versus number of stars in the universe. So these are drastically, instead of you have a function that's that complicated, right? It's that huge. Its specification would require you to spell out 2 to the m values. You are able to obtain a result for such general functions. Only property is monotonicity. For such general functions in a polynomial, by looking at it at a polynomial number of places, this is indeed impressive. Right? It's like almost being able to find one right individual by just looking at 10 people in India or something. This is that part, like the comparison should be stark and impressive as CS computer science students to us. Okay, so having sold this result enough, let me move on and systematically write down what we have done, and in particular define slightly more formally what the NV graph is, prove a property about the NV graph, and then we'll come back to the algorithm. So one sort of another comment here, note that the way we actually get to the algorithm is by establishing mathematical properties about the problem and related constructs. This is one place where the first kind of the generic statements I made early on, that these mathematical analysis is not an afterthought, it actually is a guiding light. Here, the way you are able to get to this algorithm is by actually understanding mathematical features of the problem. So this is again an important aspect. It's not a liability that I actually know the right algorithm, I just for passing the course, let me try to figure out a proof. No, in fact, it's a much simpler case. There are many more revealing examples where the mathematical machinery or the key ideas actually are critical for designing the right algorithm. Again, I hope a flavor of this sentiment gets conveyed in this particular exercise as well. So the construct we are looking at is this NV graph. So this is a directed graph with so you have a vertex in this graph, in this directed graph, for every agent. So every agent you put a vertex. It's simply the idea that you just put all the agents in a room and ask them to point to people who they envy. And so let's note that I'll define this for as the algorithm progresses, I have these subsets for different agents, AIs, but they are disjoint, so they are pairwise disjoint, but the union is still not equal to M. I have only assigned some, so at some point I had only assigned the first good, the first 4 goods, and so on. So these are partial in the sense that they do form they are disjoint and they sort of correspond to AI goes to agent I. But the word partial here emphasizes the fact that the union is still not M. I am still progressing towards a full allocation, an allocation where every object, every discrete item among the M items gets assigned. So that's the word partial here is just to emphasize that. And for every partial allocation, I can define this thing. So this here is a definition. This is a definition of this object that we are studying. So the graph has, say, some vertex set which is nothing but this, and I have a set of arcs, a set of directed edges, and here the point is that I look at a edge between two agents, two vertices I and j, and this is included in the edge set. So this is a directed edge if and only if, so I and v is j. Right, and this is the condition for NV. I looks at its own current bundle, the AI, and says, you know what, I would actually prefer J's. So if this happens, you put a directed edge between nodes I and j that represent agents I and j respectively. Okay, so yeah, this we have already seen. If you like pictures, here's the NV graph towards the end of the process that we followed for the example. Here agent 2 is NVS of agent 1 and 3. So you have these two directed edges with a directed graph with 3 vertices, 3 agents. Agent 1 and 3 are sort of satisfied. They are in fact sinks in this directed graph. Right? They don't envy anyone. So this is nothing but a general. So instead of 3, I have n agents, and instead of one, like for any partial allocation, I can define this, and I hope I don't have to like sort of convince you that this is a good object to study. It at least was very helpful in the previous example. I just now took that idea and generalized it, defined it more generally. That's all I have done. Okay, so now comes the crucial lemma, the missing piece of the puzzle, and I'll call it the shuffling lemma, and you'll see why this choice of words. And the lemma says that so I give you any collection of subsets, they are disjoint, associated appropriately with agents, so but they might or might not cover all the M elements. But you give me any such partial allocation, what I can do is I can shuffle these subsets around, and I'll explain properly what that means. So the idea is, okay, you give me any partial allocation, you give me an assignment of subsets to agents, I'll look at this assignment, and what I can do is, okay, I'll say, I can shuffle them efficiently, that is, I'll say, okay, let's exchange, I'll pick a few agents, say 3 of them, and I'll say, okay, the first agent bundle goes to the third agent's bundle goes to the second, and the second agent bundle goes to the first one, so I can shuffle them around. So still, I just reassign these bundles, if you will, such that the new, potentially new partial allocation I obtain has two very nice properties. The first one is that no one gets angry, no agent actually gets angry with this shuffle, in the sense that for every agent, possibly the new bundle it receives. So for an agent, the bundle might not change. If it does change, if it, say, agent 7 receives the bundle of agent 3, but even after this shuffle happens, the value of the agent does not decrease. This is true for all agents I in N. Right. So note that I am not changing the ingredients of AI. What I am going to do by shuffle, I mean literally a reassignment of these subsets A1 through AN among the agents. So such that with the new reassignment I have this property. So again, in the partial allocation, the BI's agent I gets BI. Right. So okay, my first question to you is that if I stop the lemma here and do not look at the second condition, I would have just wasted 2 minutes of your time. Why is that? Or 2 minutes of my time. So if I ignore this second part and I say that the lemma is I can always do this efficiently to satisfy just condition 1 in isolation, why is this not worth you coming back from lunch? What is that? Forget this source thing. I'm saying just read the lemma and stop before this and appears. So stop before bullet point 2. Do I have to change anything to actually satisfy? I just keep A as is. Do I get this property? Forget G. I mean, if you look at the first part, like if you ignore, I don't want to erase this, but let me erase this. I'm saying here's a lemma. It does not refer to the NV graph at all. It just says blah. I'm saying this is it's a bad question, not just a bad lemma. Even just asking this is not. What is that? Yeah, A satisfies it, right? I mean, fine, you just keep it as is. Everyone is greater than equal to, so if it's equal to for everyone. So it's a triviality. So fine, you in and of itself, this is nothing worth thinking about. What the nice property here is that this new B that you get, if you look at the NB graph with respect to this new partial allocation, so note that this definition is with respect to partial allocation. So A is being overloaded. The definition also is meaningful when I look at a different, it's a definition for all partial allocations. This says that if I look at the NB graph with respect to this, then this is in fact acyclic. And that's the important point, that's the sort of crucial aspect of this construction. So the proof of the lemma is actually, yeah, let me go up. So say, I mean, we were looking at 3 agents here. This was my example. Again, it was curated to ensure that I always had a source. Say that wasn't the case. At some point, what ended up happening, let's say I picked the numbers and I changed things such that, so say with 3 agents, at some point what ended up happening was agent 1 and was envying agent 2, agent 2 was envying agent 3, and agent 3 was envying agent 1. So I have some partial allocation where the 3 agents are getting A1, A2, A3 respectively. But this partial allocation gave me an NV graph that was a cycle. right? So in particular, it's not acyclic, there is a directed cycle. My question to you, what's a simple idea I can employ to get rid of this cycle and achieve the lemma? Yeah, just shuffle, like go in the opposite direction of the cycle. What you do is, okay, you look at A3 and you now assign it to, look at A1, assign it to 3. So what you do is, look, B3 becomes A1, you move in the opposite direction, fine. A3 is actually happier, right? So this NV edge, what did it mean? It meant that when B3 was looking at A3, this was less than the V3 for A1, right? This is the condition that forced you to put this directed edge right here, and so on and so forth. So my suggestion is, let's just go, like, traverse the cycle in the, yeah, like a true Indian, we go in the opposite direction of a one-way lane, and so reverse the cycle. So fine, B1 becomes A2, you kind of swap, and B2 becomes A3. So that's the update, that's the shuffle I perform. I just give every edge. So I am envious of you, I'll get your bundle. Someone else is envious of me, that person gets my bundle, and it kind of repeats. Is the process clear? So I just, yeah, rotate the cycle, if you will. But note that because of this inequality, so what I have done is B3 is A1, right? I shuffle these two subsets. So I have equality here. This is just a notational change. I'm calling B3, what was A1 is now being called as B3. So I have this, and this is the first strict inequality is because of the NV condition. So if I do this, certainly the first condition of the lemma continues to hold. Now looking at the second condition, the point though is that what you have done is you have looked at the graph and actually killed off one cycle. Once you do this reshuffling, agent 3 will not necessarily continue to NV agent 1, at least in this example. Right, so this is just an example. Let me write down the whole thing a bit properly. So proof is, so the idea is you start with a partial allocation A1 through AN, and if you look at the NV graph induced by this, if this is indeed cyclic, then sort of shuffle the subsets So you do this cycle resolution. I expressed it for 3 agents, but let's say the cycle is of k agents, nothing changes. You just kind of go, like, keep passing the subsets along, and that's it. This is sort of the idea, and I'll leave it as an exercise for you to argue that whenever you do this, the number of edges in the NV graph, so you started with A, you did this resolution, you got some other new partial allocation B. If you look at the NV graph of this new partial allocation B, the number of edges, directed edges, would have decreased. So from this A partial allocation, you sort of resolve the cycle, you say got another partial allocation B. The claim that I'm leaving it as an exercise is that the number of edges in the NV graph corresponding to this new partial allocation is less than the number of edges in the NV graph for the original, the partial allocation that you started with. In particular, this cycle has gone. The NV edges are gone. So this, what this tells me is that I cannot keep doing it over an infinite number of iterations. So every time I do this, the number of edges drops. The number of edges can be at most order n squared to begin with. It's a directed graph with n vertices. So after a poly number of steps in poly time, the number of edges, I mean, you would have to be at a graph, you'd reach a partial allocation where there is no cycle. There's no cycle to be resolved, i.e. the graph is acyclic. You don't have, you reach a final partial allocation B where the NV graph is free of cycles. So from A you go to B, you look at the NV graph, if there's a cycle you again repeat, rinse, repeat till you finally get to a partial allocation where there is no cycle. You have reached a place where the lemma holds true, and know that the first property is again sort of an induction. It's a property that continues to hold. Every time you do the cycle resolution, no one's value, no agent's value goes down, right? So stitching these observations, what you have is a proof of this lemma. So we had a idea. The idea worked when I had source vertices in the NV graph, and now in parallel I have proved to you that I can always make the graph, this NV graph, acyclic. So this is almost without loss of generality. I can work with an allocation where the graph has no cycles. How do I, how do I merge these two ideas together? Yes, yeah. So again, repeat myself. When I say the allocation is partial, I mean not all goods have been assigned. So I could have, again, it would have become a bit of a hairy example, but like say I could have been in a stage where I'm here, so G1 is still not assigned, and so this is my partial allocation. So A1 is this, A2 is G4, and A3 is G2 and G3. If I have a cycle, I could have shuffled these bundles across the agents to now get another partial allocation. In fact, a partial allocation is where the subsets actually just remain as is, the owners changed. But in this new partial allocation, there was no cycle. Right. So, okay, how does acyclicity help me? Okay, before I go to acyclicity, I skipped a particular detail, which is, I left this part as an exercise. Again, it's a instructive exercise, so I do welcome you to finish it offline. But assuming, like having faith in this lemma, trusting it as is, what is the nice property about acyclic directed graphs? Okay, let me ask a related question. Give me an example of a directed graph that has no source vertex, i.e. a directed graph where there is no vertex, where all vertices have an incoming edge. A cycle, fine, but I have an acyclic graph. So can I argue that directed acyclic graphs always have a source vertex, i.e. So my observation to you is that if you give me any directed graph that is acyclic, it does not contain a cycle, then it must necessarily contain a vertex where there is no incoming edge, i.e. there has to be a source vertex. What's the argument? This is a 4-letter word I am looking for. And we have seen it in Sperner's lemma. Perfect. It's a path argument. Right. The idea is, okay, pick an arbitrary vertex. Your graph is acyclic. Two possibilities. Either this vertex has no incoming edge, in which case you are done. Otherwise, the vertex has an incoming edge. So you go to the predecessor, you go to the vertex who's pointing to it. Fine. Now you are at a new vertex. Repeat. So you're sort of following the path, but breaking this sort of, in fact, going in the opposite direction of these one-way roads, as we typically do. So you keep on doing this, it's a finite graph, and you'll never cycle back. That is, you'll never reach back to the vertex, any of the vertices that you have encountered so far. So this is a path argument, right? It's quite similar to the room following argument that was employed in Sperner's lemma. And this is a fairly, it's not a technically deep observation, but it is a very interesting observation that the existence of EF1 actually rests on this total argument. So whenever you see an existential result, whenever you see something like blah always exists, it's very instructive to actually pinpoint the seed, very instructive to actually find out what is it that's guiding the whole thing, what's under the curtain here, what is the root idea that kind of branches into this big messy tree. The root idea here is exactly this observation. So the universal existence of EF1 allocation actually rests on this simple graph theoretic idea that every acyclic graph has a source. So this existential result with some bunch of work translates into another existential result. Existential result for EF1 stems from this idea. So it's an important idea, it's an important enough idea that there's a complexity class associated with this. It's called PPAD. That's for another day, another week. So yeah, this is sort of not just a observation in passing. This does lead to some very deep interconnections. But getting back to the point at hand, let me just repeat it one more time. So the proof of this note, this observation, is that your graph is acyclic. So you start with any vertex I. So if it's not a source vertex, i.e. there is an incoming edge, it's an edge like this, then you go to the vertex that's pointing to it. Right, you are now at a new vertex, fine. You again keep following this path. The acyclicity means that at no point of time you will get to a situation where you get back to I. Right, if you are because then that's a cycle. This cannot happen. There's a finite number of vertices. At some point of time, your efforts you will succeed, hard work will pay off, and you will have reached a source vertex, you would have reached a vertex where there is no incoming edge. Okay. Fine. So far so good. Now can I stitch everything together? Yes. Yes, yes, yes. Yes. So it could happen, like again, I kind of, this is the part of the thing that I left out as an exercise. So this claim, but you're right. I mean, of course, it can be the case that so you are at a partial allocation A. Your NV graph looks like this, and there is this isolated. So you have 6 agents. Your NV graph is like this. There are 2 of them that don't care. There's a non-vegetarian buffet. These guys are envying each other's plates. The 2 vegetarians who are happily sitting away. So what you now do is like resolve, and okay, so this guy is actually envious of this. This guy has a nice desert, say whatever. So you could happen, now what you'll do is, let's say this is A1, this is A2, A3, A4, A5, A6. So the subscript denote both the vertex, agent identity and the thing. So when you'll do the shuffle across the cycle, A1 will end up here, right? So this guy now owns A1, this guy will own A4, so on. So it might happen that this guy still now starts envying A5. So this edge that's not part of the cycle might persist on, fine. But I'm saying that no new edges, like no totally new edges will, the total number of edges will kind of strictly decrease. In particular, you would have removed these NV edges, but it does require an observation looking at all of these scenarios, and that's why I kind of didn't go. If you sit back and stare at it, you'll see that indeed, edges like this one might get shifted around, but no new NV edges. The number of edges will sort of strictly decrease, and that's sufficient for you to argue that it will terminate in polytime because you started with a polynomial number of edges. Again, yeah, so this is an aspect that I haven't, like, in the interest of time, not sort of flushed out all the details, but these are just details. Now, there's no fundamentally involved idea here. So I have 2 observations so far. The first one is that if I have a partial allocation and the corresponding NV graph has a source vertex, giving the next good to this source vertex maintains EF1. That's the reason why I soldiered through that example. The second observation is that I can do a bit of reassignment and always ensure that the NV graph is acyclic, i.e. it has a source. Armed with these 2 observations, I have an algorithm, and this is, I'll refer to as the trading cycle algorithm. The name here comes from the fact that there are connections with this and something called the top trading cycle. It's a old work by Gale and Scarf, but yeah, if you're interested, I can sort of talk about the connection offline, but that's some other classical work in sort of microeconomics. So it's just, the name is just to say that I perform these shuffles across cycles, hence that's sort of, it's one choice of calling the algorithm something. So let me just spell it out. So again, what I'm going to do now is pretty much what we have discussed so far. I'll just write it down for completeness, the entire pseudocode, so it's clear, it's there in black and white. So I start with the empty partial allocation, everyone gets nothing, and I'll also initialize so I'll keep track of the goods that are unassigned, and it's an iterative process that as I move along, I'll reduce this set capital M. So I'll keep on removing one good after the other. So keep assigning. So this is the set of goods that are unassigned at any point of time. Initially, everything is unassigned. So M is the set of all goods. And you also look at the NV graph G with this, so partial allocation A1 through AN, which is this, and So initially everyone has the empty set, there is no NV edge, it's just a graph of isolated vertices. So that's your initialization, and you kind of iterate till you have assigned all the goods. So you iterate till there's some good left unassigned. I mean, the arbitrariness of this algorithm is sometimes intriguing, in the sense that I'm actually going to pick any good. Right? That really does not matter. I don't even have to look at a choice. I just have a whole bunch of things in my Santa Claus bag. I'll pick anything, and I look at the guy who's sort of not the sort. No one is envying this person. It's like a poor kid standing in the corner, and I'll give the next good to this guy. I'll update my envy graph, shuffle these cycles around, and march on. So AI is the source vertex I have selected, and G is literally the arbitrary good which is currently unassigned. It's currently in this set M. So I'll assign, and also, like, now that G has been allocated, I'll remove it from consideration. That's the thing. I'll shuffle A to sort of, if required, to ensure that GA is acyclic. This is just, remember the lemma that this does not decrease the valuations, and I can do it, execute this step following this lemma in polytime such that this is necessarily obtained. Once I have acyclicity, it means that this particular step here can be always successfully executed. Acyclic graph will necessarily have a source vertex, so the algorithm will march on, and finally I'll just, when this set becomes empty, I've assigned all the goods. I in fact have a full allocation, not a partial allocation. Just return it. Super elegant. A piece of art here. Yeah. Why is this going to run in polytime? Right. So there's m goods. It's just sort of linear in the size of the inputs. So the loop will iterate at most m times. Every time you do, you remove a good from m. So the iteration count here, this while loop will iterate, will execute at most m times. In every loop, you are going to invoke this lemma, which is again a polytime thing. It's a cycle resolution is a efficient subroutine. There you go. It's a, right off the bat, it's a very efficient algorithm. My claim to you is that, yeah, this indeed establishes, which will now kind of do, is it will establish this theorem. It will prove that there is always an EF1 allocation, and all you require for it is monotonicity. And this is almost it's just a repetition of like what I've said. In fact, things that I've said at least twice or thrice. So still, for completeness, let's do this. So what is this proof of? It's a proof that this trading cycle algorithm, this algorithm right here, is actually going to find an EF1 algorithm, and I've already argued that this runs in polytime. If there's a question about how the algorithm works, it's a good place to ask. Otherwise, we'll kind of see the sort of argument for a final time. So the number of edges that you can create will be at most can be n.
In the worst case, you give a expensive beat that's valued by everybody to the source, and then all the edges turn it down. So the source for somebody who's not being NV.
Yes, but you can now the next good. Yeah, but probably you're right in the sense that I do like the number of edges I'll add is linear, but it's sort of it is possible. Like think of a fairly dense enough case that linear number of edges do create quite a lot of new cycles. So the cycle count might be large, but again that's not really the good measure. Yeah, the cycle resolution is like a finer analysis is worth thinking about. Far from. I think I'm being quite sloppy when I say it's like n square, it's polynomial. Yeah, it's, but yeah, worth thinking about what whether you can do it much more efficiently. Yeah. So here's sort of anecdotal evidence that at some point we are coding it up and just for our own sort of like playing around with it, and at some point we had some sort of bug that actually didn't look at all cycles, but even then it was quite successful for most of the time. Like even if we are just sampling to see cycles rather than doing like entire DFS to find cycles, and even then like the allocations were turning out to be EF1. So it is likely that in particular for the number of say the shuffles that you have, number of cycles you have to resolve to go from one partial allocation to the other, especially in light of the fact that you're already starting with you're only assigning one new good and so on. So there's structure there worth figuring out. Yeah. Right. So it will save poly and so on. So I mean, yeah. So everything is poly, but yeah, a finer grained analysis is interesting. Okay, that's the algorithm. Here's the theorem statement. Let me see if I can use my trick again. Okay, so this is the theorem I want to prove, in particular prove via by analyzing the algorithm. So essentially what I want to say is that the algorithm will always succeed, and hence not only find an allocation but in tandem prove the existence of EF1 allocations. Again, from a appreciative point of view, what's worthy to note here is that all of this, the entire existential guarantee, boils down to the fact that the acyclic graphs have a source vertex. It's almost a fairly immediate observation, but that with all this sort of steps built on it leads us to this entire theorem. So the total argument here, the guaranteed existence, is a consequence of that parity argument, the argument that acyclic graphs always admit a source. So I'll be a bit quick here because again, like most of it has been discussed multiple times. So running time is already observed, so this efficiently is fine. Note that to actually execute it, I just need to be able to figure out the NB graphs, right? So, and that entails polynomial queries to the valuations. So again, something that I'm not going to belabor too much, worth thinking about, that you can actually execute it even if you only had Oracle access to the valuation. You only had access where you would submit a set and the Oracle will tell you, for this agent the value of this set is blah. So even in that sort of model, even in that sort of adaptation of say the Robertson web model, you can very easily execute this algorithm. And what I would want to prove is that the returned or is EF1, by which I mean the final allocation, not the partial allocation, but once I have assigned all the goods, what I return, what the algorithm returns, is indeed EF1, and this is courtesy induction. So sort of the base case is when the algorithm starts, it's in fact NV free, everyone has an empty set, the NV graph is just a bunch of isolated vertices, this is fine. And now I'm going to say that consider the tth iteration of the while loop. So in this, I'm looking at this thing, the while loop, and as it executes, I stop it at the tth iteration, and then I'm going to analyze the fact that EF1 continues to hold. So by the inductive hypothesis, it held before this iteration. I just want to argue that it continues to hold after the iteration. So it's a proof by induction. So the superscript is now the timestamp t. So this is the partial allocation before the tth iteration. So this is EF1 by the inductive hypothesis. Now what happens is say with G so in this tth iteration, this specific good G gets assigned to this agent I. I'm just setting up notation here. Okay, so what does this mean? This means that the new partial allocation is going to be, so again, superscripts denote iteration count. So how does this bundle compare to this bundle? What is that? I mean, what's the connection? This is equal to this plus, what do I write next? I is the agent that receives this, G is the good that gets assigned. What is that? What is that? Union G, yeah. So that's it. And for every other agent, nothing stays the same. So, okay. So it's pretty much the thing that I've in fact had written up. So I look at any other agent, I look at J. So there are two cases. So the first case is I'm considering J and I. So why do I have this inequality? what is special about I? So that's it, right? The I is a source vertex. This graph, so I picked I in the while loop because it was the source vertex, so I have this inequality. There was no, j was certainly, any j wasn't envious of I. So again, this is just the definition of what, how the bundle of I gets updated. So if I look at two agents that are, both of them are not equal to I, it's just EF1 property is already there and the bundles haven't changed. So this is directly by the induction hypothesis. And finally, the case of, I consider I and j, what I have is, this is by monotonicity. And the last inequality is because for j not equal to I, the set hasn't changed. So it was, if it was EF1 to begin with, it will continue to be EF1, the choice of the good stays as is. These are like kind of, yeah, if you followed along the ideas, I'm just writing them in a precise formal manner. If it might look like a whole bunch of notation, but I guess if nothing else through this, you should be able to appreciate like this. It's just conveying those ideas in sort of in an equation form. Okay. Yeah, I cannot impress upon you the fact, the level of generality of this having having a result with this broad sort of so like this is too quite general. As computer scientists or as like looking at getting this sort of generic results is impressive, at least to me. So it's hard to find like non-trivial results with this such a broad scope. So this is an impressive result, and in a sort of a relative sense, the proof is quite direct. I mean, there are formal constructs here, but yeah, the ideas are kind of clean. So how much time do I have now? Okay, sure. So I have 15-20 minutes. Okay, I'll do one more result and then we'll kind of call it that. Yeah, so let's talk about, let's restrict ourselves to additive valuations. And actually, let me go back to the example and sort of remind you that specific example. So here it is in smaller font, here it is in bigger font. And so the valuations here are additive. We developed an algorithm that worked not just for additive, but in fact for monotone valuations. So certainly it does address this example. But now let me sort of come back and tell you that, look, I actually could have made your life easier. If I am sticking to additive valuations, there was in some sense there was a simpler algorithm that I could have discussed and called it a day. But I really did want to go over monotonic valuations. I did want to impress upon you the fact that EF1, these fair solutions exist in sort of vast levels of generality, let's circle back to our example, circle back to the case of additive valuations and just sort of, yeah, spice things up, or say that, look, in some sense, I made you work a bit harder than required if additive valuations is what you are, is all that you are interested in. And I'll give you a very simple algorithm to find EF1 allocations under the sort of limited range, under the limited class of additive valuation. So, as we have seen, what good is a theorem if you don't have 2 or 3 proofs of it? So, you can think of it as a second proof of existence in computation of EF1 allocations for under additive valuations. So, the second theorem, if you will. So note that if I, like, again, this is in fact as is, it's just a corollary of the previous theorem, right? Additive valuations with non-negative values are monotonic, and hence this is, I'm not actually giving you a sort of, so in that sense this is if I stop my theorem statement here, this is nothing new. You already have this as a consequence of the previous theorem. The differentiating feature is the method, by the algorithm by which you can do this. What I'm trying to say here is that, look, there's actually a very natural algorithm when you are in the world of additive valuations. There's a very natural algorithm that achieves EF1. The algorithm is round robin. What I'll do is I will have the buffet of discrete indivisible goods on the table. I'll order every one of these n agents in some way. So just order them, say 1 through n, and I'll say, okay, please form a queue. Every agent comes to the buffet table of these indivisible items, picks exactly one of these indivisible items, say the item that it likes the most, and goes back to the end of the queue. So it's just a round robin method. I kind of go over these agents in a round robin fashion and just let them select one, like the choice good, one after the other. So, before the proof, I will actually. So again, M is the set of unassigned goods that sort of keeps getting updated or reduced as the algorithm progresses. So I just keep running this for loop, right? So if at any point of time there's no good left, you stop the process. I mean, like the agents aren't there to stare at a blank table. So that's sort of the obvious condition. But say this is not the case, there's some good left unassigned, M is not empty. What you'll do is, So look at all the goods that are unassigned. So you're doing this argmax operation over the unassigned goods. Argmax means, well, you're just picking the good that achieves this maximum, and the good with the largest value. This is simply saying this is i's turn, so you're going in a round robin fashion. When i's turn comes in, I looks at the set of unassigned goods, m, among them picks the one that it values the most, the one that has maximum VIG, and that's it, gets to select it. So what you do is you update just add it. So AI has made a selection, and this get good is now off the table. You remove this good from your set M and you are good to go. That's it. The round robin executed with just this simple greedy choice. Again, this is not something I'll be able to substantiate in the interest of time. Round robin is a very interesting algorithm in the context of discrete fair division. The problems for which you would imagine that this thing won't work, something, again, let me throw a jargon here, something called submodular Maximin fair division under submodular functions. Round robin, in fact, ends up being successful even then. There's a stronger solution concept called EFX. When the valuations are identical, a modification of round robin works. So if, say, at some point you are forced to design an algorithm for fair division of discrete indivisible goods and you are uninterested, a good heuristic to follow is the round robin method. So that's sort of, there's one takeaway, and at some point of time you actually do run into like doing things fairly. My sort of meta advice to you is try the round robin. This simple looking algorithm succeeds more often than not. And arguably this is a method that you would have, one has a natural appeal to it. Right. This is one of these cases where a simple algorithm actually ends up admitting a nice proof. Yeah, this is completely arbitrary. The ordering here among the agents does not matter. You can just shuffle them, so order the agents any which way you like. The algorithm is going to succeed. The only selection rule that you're following is when the agent gets to pick, when it's I's turn, it's the best, the most valued good for I that gets included in AI. No, I mean, you could have a case where you just, like everyone values something, there's no overlap. So it doesn't matter if you go before me or after me, you will end up there. Yeah, so there are three of us, there are three distinct goods. Yeah. So there are cases where there's just a unique EF1, so it doesn't matter. Okay, so that's the algorithm, and here's the proof of correctness. So I have m goods, and one after the other these m goods get selected. All I'm doing right now is again a notational setup. I'm just indexing them in the order they got selected. So G1 is the first good that got picked up. Note that what this means is at the first iteration it's I is equal to 1, it's agent 1's turn, and so agent 1 among all the goods picked G1. So based on this selection rule, you can be sure that for agent 1, G1 was the most valuable good. Right? Agent 1 has at its disposal the entire buffet, and he went after the dessert, picked this good G1. So eat your dessert first, I guess. So G1 is the first good that got selected, G2 is the second good, so agent 2 picks G2, yada yada yada, Gn is the nth good that got selected. Now again, this is the indexing is the way the goods make an appearance in the algorithm. I look at the next good, Gn plus 1, who owns this good? So this is the n plus 1th good that got selected as the algorithm proceeds. Who's the owner of this good? Agent 1, right? You have circled back and it's agent 1's turn to pick again and it picked it. So if I were to write it as a picture, A1 would look something like G1, A2, I have AI, so it's GI, AN plus AN is GN. Note that I am indexing them to exactly align in this crisp manner. That's just an indexing, right? I really don't care what the names or the identities are. I am just for notational convenience, I'm calling the good that got picked in the tth iteration GT, so on and so forth. So how many times will this algorithm iterate? What's the iteration count of this algorithm? M times, right? You just, every time one good goes out of contention, this G hat is kicked out, so it's M times. Right, so this is the first round of the round robin. Everyone picks one. You kind of go up and Gn plus 1 goes here. Right, it's the agent 1's turn again and she ends up picking this good, courtesy the indexing. This is Gn plus 2, this is G2n, right. So that's the second round of my round robin. It will kind of proceed till some point of time where Gm gets assigned and these guys sort of things stop. So note that a nice property that holds up front is that if you look at the difference of the cardinalities of any two subsets that have emerged, AI and AJ, they'll differ by at most 1. Right? In each round, everyone got 1. It might be the case that M is not divisible by N, so you'll have a tail hanging around. So there's a difference of 1, but okay, to begin with, at least in that sense, it's a fair partition. Like if you look at the count of things you have obtained, this is just plus minus 1 of any other person. That's a trivial observation, but okay, get things started. Right, the cardinalities are itself quite close. It's not like some guy is getting a very large number of goods versus some guy is getting a very fairly small number of goods. Again, a good instructive exercise once we finish this is to actually come up with examples where for additive valuations, if you execute the cycle resolution algorithm, you end up with a very different EF1 allocation versus round robin. Note that this cardinality property was no way guaranteed in the other one, where it is here. Again, if you are interested, I can tell you some useful properties that pop out of it. In particular, you can put this observation on steroids and get something like existence of EF1 under what are called matroids. Again, if you are interested, we can discuss this offline. That's just a passing remark to sort of ease you into what's happening. Fine, so this is what the partition looks like. I've indexed it so that things kind of match out cleanly. But here's the nice observation. So let's just so I start by looking at agent 1 and recall that very crucially that the valuations of all the agents are additive. So I start by considering agent 1 And my claim to you is that, you know what, this guy not only is satisfying EF1, agent 1 is envy free. Like he got to go first in every round, and that ensures that what he has obtained is quite good for agent 1. And the observation is that let's just do this argument round by round, right? So let's just look at round 1. When I say round, I mean the one loop through all the agents. So I goes from 1 to n. Now if you want to be very pedantic, it's actually not for I equal to 1 to n. Okay, if I write this algorithm in a coding exam, why would I fail? I should get a hackathons would kill me out. Well, this would just run once, right? This will not return. A for loop for I goes to 1 to n, it will terminate. So yeah. Yeah, so okay, slight abuse of notation, the agents are indexed 0 to n minus 1. So yeah, what I said was morally correct. Figure it out. You guys are like, you can code, huh? You want me to do this, huh? Okay, here you go. Correct piece of pseudocode. You just do mod n. So it will keep circulating through all the agents 1 through n. Okay, so when I say a round, I mean like a sequence of n steps where from agent 1 to agent n, everyone picks a good. In this picture, this means this entire phase, like going from G1, G2 to Gn. So I look at round 1 and I note that if I have this, then this is at least V1 of Gi for all in fact, I don't even have to put this upper bound here, but let's say I do, just for be a bit more specific. Why do I have this inequality? Why can I say that G1 is valued the most by agent 1? Selection rule, right? Like agent 1 had the whole buffet, luxury of picking anything, went ahead and picked G1. So obviously liked G1, which means that if I stop at this round, the agent has actually envy free, right? If I stopped right here when the first n goods are assigned, it's envy free, right? But it repeats, like look at this good Gn plus 1, the same argument. All of these Gn plus 2 to G2n were assigned afterwards in later iterations, and hence like V1 of Gn plus t. So this is the good that one gets in round t is, yeah, I mean, let me just write it 1 for the second round. And this is round 2. Fine. So good by good, if you sort of go down this list, and agent 1 is quite happy. It was always getting to pick its best, its first choice. This is exactly and the only place I'm going to use additivity. The fact that I have this good-wise comparison, additivity tells me that I can sum it up. The value that agent 1 has for this bundle is going to be never less than the set of goods that are assigned to any other agent, because if I look at the round by round, agent 1 is doing quite well. So what I have is, so again focusing on agent 1, V1 of A1 is in fact V1 of AI for all agents I. I in fact have NV freeness, right? My claim to you is that if I look at a pair of agents, say I and J, and I in fact comes before agent J, I'll never have NV. So in that sense, the NV here is only going to be upwards. It's only going to be towards someone that pushed you in the queue and went ahead in the round robin algorithm, right? So, and my claim to you is that even then it remains EF1, even then you'll not sort of have NV beyond one good. And again, I think I'm enjoying this trick too much. Okay, so this is my allocation. Again, recollect the indexing. So now I'm like just going to sort of generalize it to any other agent and complete the proof. So, so pick any agent I, fix any agent I. Now, so here I have, this is going to be Gn plus I, G2n plus I, and so on. Again, courtesy my indexing. So note that it is possible that if I look at this point of time, if I look at AI, then I is envious of one of the agents whose index is smaller than I, right? So it is possible. It's possible that like V of, so Gi is the good that agent I got to select in the first round of the round robin. It's possible that this is of value less than say G1, right? Possible, right? Because G1 is gone. By the time I came to the round robin buffet, one having nudged everyone was already up ahead, right? So fine, okay. But what's not going to ever happen is that this value is in fact less than the second good that agent 1 gets to pick. Gn plus 1 was selected in a later iteration, it was selected in a second round. So when I was about to select, Gn plus 1 was in the unassigned set capital M. So though we always have Vi of Gi, at least Vi of Gn plus I, n plus 1 in fact. So, right, I'm trying to compare I and looking at a agent. For now I'm fixing 1, but you can repeat it for any agent whose index is smaller than I, right? So, but this will never happen because again it's a trivial selection rule. When I was about to select, why didn't it then not select Gn plus 1? Okay, but that's it. I mean the picture is that this is of value more than this will be of value more than like, so this is 2n plus 1, this is 3n plus 1, but you'll continue to have, so you might not be able to compare with the good in the same round, but you can compare to the good in the next round, in the round robin. So you have these comparisons. By this arrow I mean the value is greater. It's not an NV edge, please. But again, the valuations are additive, which means if you sum it across, you are good to go. What's left is just one single good that actually made an appearance before you showed up. So If you look at AI, again, I am going to use the fact that once I have this good-wise comparison, I can sum it up and that will give me this. There's at least Vi of say A1 minus G1. So it's not just NB free up to one good, it's NB free up to the good that was selected before you got to the round robin table, right? So it's that very specific. In fact, it's always NB free with respect to the one of the first n goods that got assigned. So modulo that, you have this. So this I just argued with respect to A1, but what you have is for any agent J that with index smaller than I, which means J actually gets to go before I in every round in the round robin. What you have is, this is Vi Aj specifically Gj, the good. So Aj is somewhere here, Gj is this good, and in the complementary case of goods after I, again we have already discussed, is in fact NV free. Forget EF1, it's legit NV free. So that's it. Yeah. It's sort of, you can think about like efficient data structures and such for doing it quite efficiently. Yeah. So again, you're doing this max exercise. It's like some sort of a heap and all would probably work. And as I said, like the allocation is quite balanced in terms of cardinality. It is robust. I mean, this idea does translate into some other interesting settings. The fact that there is a specific ordering, there's a specific good, so on and so forth. So that kind of is a good property to notice. Bit right. So the number of pairs that have NV can be at most, like the person can NV, so like you might be the case that this is sort of there for all. So in the worst case, I do think there'll be, yeah. Right. So it's a hard problem. So I guess the question is, let's try to be a bit more, like set higher goals. So among possibly many EF1 allocation, find the one where the now NV is as between the pairs is minimized. So I mean the partition problem reduces to it. So if there is, for example, if there is an NV free, that's sort of equivalent to determining whether there is an NV free allocation, and that's a hard problem. But that's when it's 0. Yeah, so, okay. Here's a parting gift for you. So it's computationally hard to, I give you a discrete fair division instance, like problem with additive valuation and agents M goods, determining if it admits a NV-free allocation is, this is an NP-hard problem, a fairly simple reduction. So if I tell you the problem, okay, try reducing partition to it. Okay, yeah, let's stop here. Thanks.